Hello, everyone. Today, we're going to talk about the Weil pairing. Before, we've talked about isogeny, the dual isogeny, and we talked in the last lecture about inverse limits and the Tate module. I wanted to mention that I gave a rather restricted definition of inverse limit, where, remember, in our definition of inverse limit, there was a chain of groups going in one direction and every one was connected. You can do that in a much more general setting of inverse limits, where the maps are just indexed, or the groups are indexed by a partially ordered set, and then there are maps going down only when those two indices are related. So for example, Z mod NZ, if you take your groups to be Z mod NZ, then there is no map between Z mod P and Z mod Q, but there is a map between Z mod PQ and Z mod P and Z mod PQ and Z mod Q. And you can do an inverse limit like that. When you do that, you get a different inverse limit. So for example, you can do the inverse limit of Z mod NZ. And now those are vectors indexed by integers, and each coefficient is a number modulo n. And in just when a congruence can happen between two numbers, those numbers have to agree. And with that, we call that Z hat. That's called the profinite completion of the integers. And similarly, you can do that for all the roots of unity, and you get the Tate module as a Z hat module of Q. So you can do T mu, and you get the limit as the inverse limit of nth roots of unity. And that's the full Tate module. And now it's a Z hat module. And you can do also for elliptic curves, if you do the inverse limit of n torsion, then you get what we call the adelic Tate module. It's again a Z hat module, now of rank 2. Okay, so that is a more general construction that encompasses all the other p-adic Tate modules as well, just by there are maps down to those. I just gave a talk in Zagreb, in the University of Zagreb. I was home in the same place I am right now, but an hour ago I gave a talk about adelic Galois representations, and I'm going to put that video as part of this lecture. So in fact, it's going to show up in the chain, or in the YouTube channel. It's going to be before this one. There's going to be sort of like an optional lecture that you can watch if you want to learn a little bit more about what's known about adelic Galois representations and a little bit about the p-adic Galois representations. I think it's at the level that with the lectures you've seen so far, you should be able to understand most of what's happening in there. And it features some work with previous graduate students from UConn and current, like the work of Garance for his thesis is featured in that lecture. So you can watch that. All right, so today what we're going to do is talk about the Weil pairing, which is a gadget, which is a quite peculiar gadget. So this is named after Weil, after André Weil, a French mathematician, and it's quite a peculiar gadget that is going to be quite complicated to construct to prove the existence of the Weil pairing. But then once you construct it, usually you just completely forget about the way it's constructed, and the usefulness of it is its existence is what people usually call, and you'll see it in research papers and other places, that by the existence of the Weil pairing, or by the properties of the Weil pairing, this or that happens. But it's worth exploring, like why the existence itself. So we're going to start by recalling. So I need a before I construct the Weil pairing, I need a result. So let me first recall that we have an isomorphism between the Picard zero of E and E itself. And remember that the map sends the class of a divisor in Picard is sensitive to P, and P is the unique point on the elliptic curve such that D is equivalent modulo principal divisors to P minus O. Okay, there was such a, that we proved, and we used that to sort of like compare the group structure between Picard and E. All right, so what we're going to do today first, I'm going to prove something that is actually quite a natural question, which is, suppose you have an elliptic curve and you have a divisor of degree 0. We know the principal divisors have degree 0. So you can ask yourself, if I have a divisor of degree 0, when is it a principal divisor? And the answer is that for elliptic curves, these principal, if and only if, the sum of the points, and this is the addition on the elliptic curves, so this is happening, this is addition on E. If you add those points, so here, remember that this sum is just a formal sum. There is no actual addition of points happening. But now on the elliptic curve, I have an addition. So if you add the points according to the coefficients of the divisor, if they give you 0, then it is actually the divisor of a function. So let's start with a proof of that. So, so here's the proof. It's not that difficult. So if D is principal, then D is equivalent to the 0 divisor. This is if and only if, by sigma, sigma is an isomorphism, so sigma of a principal divisor has to go to 0. So sigma of D is O, the origin on the elliptic curve. And this will happen if and only if, well, I can substitute my definition of D. So sigma of the sum of NP times P for P and E, this is O, right? That's just the definition of the divisor. This is equivalent to the sigma of the sum of NP times P minus the sum of NP times O. Is 0. Why is this? This is because I've only added 0 here. I've added 0 to itself, to the previous equation, because the sum of NP is just, so here, maybe if you want, we can put a parenthesis here. This is just a number, which is 0. Okay. So here, we know that the degree is 0. The degree of D is 0, and therefore the sum of the NPs is just 0. So I can add 0 if I want to that divisor. That doesn't do anything, but it does help me that I can rewrite this as NP times P minus O. So basically I can bring an O if I want to, like this. And this is O. And now sigma is an isomorphism of groups, so sigma can go inside, and this is even only if the sum of NPs times sigma of P minus O is O. And now we know what sigma of P minus O is. If P minus O, if now the divisor, the unique divisor, so D is P minus O, then sigma of P minus O has to be the unique point such that this divisor is equivalent to P minus O. So it's got to be P. So the image of this is P. So this maps to P via sigma, and therefore this is just saying that sigma NP times P is O. Okay, now in the very last line, the addition, this addition now is actually happening on the elliptic curve. So I'm going to write it like multiplying by MP is the multiplication by NP map, or the multiplication by MP endomorphism. So I can write it like this just to make clear that this is happening addition on O. So I'm done with my proof that D is principal if and only if the sum of the points is O. Okay, great. So that gives me a criterion to know when a divisor is the actual divisor of a function. A divisor of degree 0 is a divisor of a function. So now I can use that to construct the Weil pairing. So construction of the Weil pairing. And you'll see it's quite complicated, but it works. Quite an interesting construction. So let's start with an elliptic curve. And let's let T be a point of M torsion. Okay. And consider the divisor M times T minus M times O. Notice that if I actually add those points, M times T minus M times O, what do I get? T is of M torsion point, so this is O minus O equals O. So they add up to 0. The degree is 0, and the degree of this divisor is M minus M equals 0. So it is a principal divisor by the previous corollary. Okay, so the corollary tells me that there is a divisor. So there is a function in the function field of E such that the divisor of F is precisely MT minus MO. Perfect. I don't know what that function is, but there it is. Later on, much later on, we will actually construct functions with these divisors, but that will wait until chapter 10 or something in the book. Okay, so now let T prime on E be such that it's going to be an mth root of T. So a point such that M times T prime is T. Okay. There is such a point, by the way. Remember that M is a non-constant isogeny, and therefore it is surjective. In K bar, okay, this T prime, who knows where it lives, but it's in K bar, it exists. There is a point that maps to T under M, under multiplication by M. Okay. So now here is another divisor. I'm going to construct another function with the following divisor. Is going to be what we called M star T minus M star of O, where recall if I have an isogeny phi star of Q of the divisor supported at Q was the ramification divisor for phi, which was the sum ramification index at P times P over P in the fiber of Q. Okay, but the multiplication by M map are unramified. So it's just a sum of preimages, okay? So this is just, this divisor is simply the sum of preimages of T. There's gonna be M squared preimages, and actually all the preimages are going to be of the form like, I have one preimage of T plus M torsion points. All of those under multiplication by M are going to map to T. So actually, if you think about it, they're all of this form, T prime plus R for R and M torsion point. Those are all the preimages of T. Minus, what are the preimages of all? Those are the M torsion points. Okay, so here's a divisor. What happens if I, first of all, how many, what's the degree? So there are two things to notice. The degree is 0 in the two sums that are here. There is as many points, as many entries as there are points in the M torsion. So it's M squared minus M squared. It's 0. And on the other hand, what happens if I add all these points? What happens if I add all those points? I get yeah, cool. So what happens if I add all those points? I was a little bit confused. So what happens if I add the points T prime plus R minus R? But clearly this is over all M torsion points and over all M torsion points. Clearly the M torsion points are going to go away. So I just have a sum of T prime, just a sum of T prime really, right? The R and the R are going to cancel out. So what I have is a sum of T prime over R in M torsion points. That's strange. Well, there's no R in that sum, so it's just as many copies of T prime as there are points on EM, but I said there are M squared of those. So this is M squared times T prime. I know what M times T prime is T. So this is M times T. And I know what that is because T was a torsion point of order M. So this is O. Oh, nice. So all the points add up to 0. The degree is 0. Therefore, by the corollary, once again, what happens? There's got to be a function that divisor is the divisor of a function. So there is a function G such that the divisor of G is that divisor, the sum of T primes plus R minus the sum of R for R in EM. Okay. All right. So we have a function F, we have a function G. Notice that both the function F and G, all the information that it took to construct them is this point T. So they actually depend on a point T, how they were constructed, but in any case, here they are. So let me write those. Again, there is F such that the divisor of F is M times T minus M times O with T in EM. and a G such that the divisor of G was M star. So is the sum of T prime plus R minus the sum of R. And here is R is running over M torsion points. Okay. So now note that what happens if I consider the divisor of G to the mth power is going to be M times the divisor of G. That's easy. That's the sum of M times T prime plus R minus M times R for R running over M torsion points, right? But how about the divisor of F composed with multiplication by M? What is that? Well, now the divisor of that is actually going to be M times the divisor of F. Not the divisor of F. It's actually going to be also M times the sum of T prime plus R minus R over R in EM. Why is that? Because, so consider like what are going to be the zeros of F composed with M? The zeros of F composed with M are going to be when is F. So why is this? Let's see. So we have F composed with M of some point Q. So if this is 0, then what that means is that F of M times Q is 0. Okay, we know what the zeros of M are. The zeros of M are, well, they're right here. The zeros of F is just the point T. Okay, but there is a zero of F at T of order M. So to know what are the zeros of F composed M, I need to know what points under multiplication by M go to T. But the points under multiplication by M that goes to T are the preimages of T under M, which are precisely these points. And each one of those will have a zero of order M. Okay. Similarly, what are the poles of F composed with M? Well, I know the poles of F itself are, there's only one pole at O of order M. So I need to know what points go to O under M. Those are the preimages of O under multiplication by M, which are the M torsion points. And there will be a pole of order M for each one of those. Okay. This takes a little bit to digest, so you can pause the video if you're watching this, or if you're live in the classroom, then you're stuck and you have to just think quick. So anyway, this, if you think about it for a second, for probably more than a second, a minute, this is the divisor of F composed with M. And now you notice that these two things are equal. They're the same thing, okay? What does this mean? That means that if they have the same divisor, two functions with the same divisor differ by a constant. Okay, so this implies that that F composed with M and G to the nth power differ by a factor of something in K star. Okay, so that says that F multiplied f composed with m is lambda times g to the m. So might as well change f by that constant so they are equal. So I can pick f so that f composed with m is precisely g to the mth power. All right, we're about halfway there in the construction of the wave pairing, almost there. But this is the key. These two functions are related by that formula. All right, so now I have functions f and g that are related by this formula. Okay, so now we throw in a second point s of order m. Remember that there was a point t of order m floating around, and t actually comes in defining f and g. Okay, so f and g depend on t. So t is in the background, lurking in the background. It's there. It's not completely obvious, but it is there. Now I have another point s, and for any, this is the tricky part, I'm going to pick any x point on E. Consider the following. G evaluated at x plus s to the mth power. What is that? This is, I know that g to the mth power is f composed with m. So this is f composed with m evaluated at x plus s. Okay. And then I can distribute multiplication by m. So this is f of m times x plus m times s. Guess what? S is an m torsion point, so m times s is 0. So this is just f composed with m evaluated at x. But f composed with m is f composed with m, which turns out to be g to the m. So this is g evaluated at x to the mth power. Okay. If so, then that tells me that, for example, that g x plus s over g x to the mth power gives me 1. Huh. That is some number. G evaluated at points is just giving me a number in k bar. So that value of g over g to the mth power gives me 1. That means that g x plus s over g x is a root of unity, is an mth root of unity in k bar. Okay. Moreover, the map, what happens with the map? I chose an x, right? I chose an x on E, so who knows? Every time I choose a different x, I might get a different root of unity. I'm going to prove that actually this is constant, so I'm always getting the same root of unity. So moreover, the map from E to P1 defined by x sends to, let's say, in affine to g x plus s over g of x. This is a morphism. This map is a rational map, but E is smooth. So this is a priori some rational map, but E is smooth. And remember that a rational map from a smooth map, at every smooth point has to be a morphism at that point, or regular at that point. So this has to be a morphism. So this is a morphism. And remember that morphisms are either constant or surjective. But this is a morphism And this we prove this is a root of unity with values in mu m, which certainly it is not all of k bar. At least if the characteristic is 0, this is an algebraic closure is infinite. So the nth roots of unity are not all of it. So it cannot be surjective. So this is not surjective. Therefore, it is constant. So it doesn't depend on x. So there you go. So I've constructed a root of unity out of all this mess. We've constructed a root of unity. So this is a constant with respect to x. Okay, well, I have not said what happens with s. So I have a root of unity that depends only on s and t. Remember that G encodes t in a tricky way. All right, so we're ready. Here's the definition of the Weil pairing. The definition of the Weil pairing is the following: is a pairing from where to where? Remember, I had an M torsion point cross M torsion point. Okay, I had a point T originally and a point S, and it is going to roots of unity of your field K. Okay. And the map sends a pair of torsion points to the value G of x plus s over G of x. And remember again, this G is depends on T. So that's where the T comes in. It seems like the T disappears, but the T is there implicitly. And this is called the Weil pairing. This is the mth Weil pairing on the M torsion. Fantastic. So as I said at the beginning of the lecture, the devil is in the details of like what are the properties that the Weil pairing satisfies. So let me maybe just stop here to breathe and drink a little bit, and then we'll continue the second part of the lecture with the properties of the Weil pairing.